All right, guys, today we are going to do our one day, just little mini lesson on vectors. Really, today is just a preview of what we would, a small segment of what we would normally do. Obviously, given our time constraints, we won't have time to do everything, but we want to show you enough that at least you'll know what it is going into calculus. You'll be using it more there, and actually, you'll use it a lot in physics. So if you've already taken physics, you may already know a little bit about vectors. If you haven't, plan to learn some more about them. There's actually quite a few applications of vectors. Again, really the thing with the vector is it has both a magnitude, that's like the distance, the length on there. A lot of times that could be speed, and direction. So, I mean, one example of this could even be applied to like sports. If you think about hitting a baseball from a bat. It has a direction and it has a speed. We think about it with vectors on there. So a couple of the definitions that I want you to know. Every vector has an initial point. Again, that's where it's starting. And then the terminal point, that's where it ends there. In the coordinate plane, if we're thinking about the initial point at the origin, that's what we consider our standard position. A lot like what our standard position is when we think of a lot of our trig angles, and you'll see a lot of that's kind of similar because the direction of the vector is actually our angle. We're actually going to be doing angles in degrees. Typically, when we're doing things in physics, as a lot of you know, I know we would go back and forth between degree mode and radian mode. We think about it in terms of degrees instead, and that's the angle between the vector and the positive x-axis, and it's always going in the positive direction. So think about it going counterclockwise, and we'll get to that in a little bit there. So the length of the line segment is the magnitude. So actually what we do for that notation is it's actually absolute value. Again, I'll show you that in a little bit. So we have component form of the vector. There's a horizontal component and a vertical component. And you'll see that there's a new notation. If you look right here, it's not parentheses. It's a different kind of a notation, and I'll show you what I mean by that. So these are some examples of vectors. It doesn't look very good on my end. Hopefully it looks a little better on yours. Vectors, when you look at them, they have a little arrow going on the top of it. Sometimes you will see, it depends on where you'll see it written and different type things. A lot of times you'll also see it as just a bolded letter, like we wrote that down here. The vectors, that bold A and that A with the arrow on top. A lot of times those are just, interchanged there. It just depends on where you've seen it typed. I've seen different textbooks do it different way. The way we're going to show it right here is with the arrow. Again, for some reason, when it converted to this PDF form, the arrow looks a little weird on the top of some of these, but I think yours should probably look a little bit better. All right, so let's look at one of these here. If we look at vector A is actually in standard position. Again, that means that the initial side is, the initial point is on the origin, and our terminal point then is over here. So with the initial point at the origin, it's in standard position. But really, when we get to all the other ones, you'll see that they're called free vectors. It doesn't really matter where we put it, and I'll get to that in a little bit here. But this first one's in our standard position. So really, to come up with some of these things on here, I'm going to actually start with the magnitude because I think a lot of you probably already are looking at this like I can figure out how long that vector is, because really this just creates a right triangle. And we know how to do things with right triangles. We know that the length of this horizontal part right here is 5. And the length of this vertical part, or really our leg, is 3. So if I do good old Pythagorean theorem, 5 squared plus 3 squared, that's 25 plus 9, or that gives us 34. That's going to give us, or the square root of that is going to give us the length of that arrow going along the way here. So that is our magnitude, the square root of 34. That's all there is to it. Just really finding that hypotenuse along the way there. Okay. Component form. Again, when we write our component form, we don't write it as an ordered pair per se, because it has that different notation along the way here. But it's really the same kind of idea. It has a horizontal component and a vertical component. So if we're at that first starting point right here, okay, if we're at that initial position there, the initial point, it's going to the right 5, so the horizontal component is 5, and then it's going up 3, So our vertical component is 3. This is how we write component form. That's all there is to it. So now direction. Again, I mentioned before, direction is really the angle. And again, it's the angle from the positive x-axis going in a counterclockwise direction. We've really done that before. We've done that with trig. That's just like our regular angles that we're looking at. So I'm really looking for this angle in here. Okay, so we can just use trig to find that angle. So I know that the tangent of that angle has to be the opposite over the adjacent. So we can use the inverse tangent and use our calculator for this. You'll get your calculator for this. And again, we want to actually be in degree mode. So change your calculator into degree mode. And we're going to round to the nearest tenth. So that gives us an angle measure of 31.0 degrees. I am going to write the 0.0 on here to round to the nearest tenth. And that is the direction. So it's just telling us, since it's 31 degrees, that really it's in quadrant 1 right there. That's a quadrant 1 angle, so that's that vector is going in that direction. So that's kind of gives us that information on the direction. Okay, now if I look at B, going over and looking at B, it's not in standard position, right? The initial point is not on the origin right there. But what we can think about, again, what these are called is free vectors. That means it really doesn't matter where you put them on the whole coordinate plane. It doesn't affect your component form, your magnitude, or your direction. So what that means is I'm actually going to kind of think of this as, what if I were to put it in basically standard form? I'm going to think of this kind of blue part right here that I'm drawing in as like my origin. So if I were to make that really, that's the initial point, think about that as being at the origin right there. Okay, that just kind of helps us think through some of these points along the way, because really everything else is the same idea within there. So, ooh, sorry about that, guys. So if I look at this as a triangle, okay, this going to the right, this distance is 4, the horizontal distance is 4, and our vertical distance is 1. It goes down 1 right there. So to write this in component form, again, it doesn't matter where it is on the coordinate axis. It's still going from that initial point. So from that initial point, it goes to the right 4, and it goes down 1. That's our component form. Okay, going to that terminal point at the end of the arrow there. Okay, so now thinking about the magnitude, again, we're just going to do Pythagorean theorem. I'm going to do it in my head. So 4 squared plus 1 squared is 17. So the square root of that, Pythagorean theorem, gives us that hypotenuse, or the magnitude of our vector. Now for direction, this one we're going to have to think about a little bit here, because for our direction, again, it's from the positive x-axis going in a counterclockwise direction. That actually means, if you see what I just drew in here, we want that full, almost all the way around the circle right here. Okay, so what we need to find is this little angle right here. But we can do that just using trig. Okay, if I move it over here. So that means, again, we're going to do the tangent. So the tangent of whatever that angle is, that's what we're trying to find. I'm not going to call that theta right here, just because that's really the direction that we're thinking of, but is the opposite over adjacent. So if we're doing the inverse tangent on it, again, we would use our calculator. The angle that we get for that is 14.0 degrees. Okay, so if we look at that, just to kind of think, let me make it even bigger. I guess that's not that much bigger, but a little bit less congested over there. That means that this angle right here is 14.0 degrees. We want to know the rest of the whole way around. So if all the way around the circle is 360 degrees, we're going to have to do 360 degrees minus that 14, and that's where we come up with 346 degrees. Again, I'm going to say 346.0 degrees. That was the 360 minus the 14. Again, we have to do the entire direction. That really tells us, again, that that vector is going in that specific direction. If we were to think about it in quadrants, it would basically look like it would be in quadrant 4. Now, I know that's not where it's drawn on the coordinate axes over here, but that tells us our direction there, that it's 346 degrees. All right, what I want you to do, I want you to maybe pause this, see if you can try C and D. I'll still go through them, but maybe pause them, try them on your own, and see what you can do. Okay, if you paused it, great. If not, I know some of you are not doing that, and that's okay. But let's see it. Look at C here. Again, this is my initial point. Again, I'm going to think about this as kind of my new axes. I'm going to put that in standard position right here, just to kind of help me think through it. If I draw this in, the horizontal is going 3 to the left. The vertical is going 3 up. So my component form, it went left 3 and up 3. So that negative 3, 3. Okay, you may have noticed that this was a special kind of triangle. Hopefully you noticed that really this is a 45, 45, 90 triangle. Now you could use Pythagorean theorem for this, or you can also remember that if the leg is 3, that means the hypotenuse is that leg times root 2, so 3 root 2. If you didn't remember that, that's okay. You could do 3 squared plus 3 squared. That would give you 18, and the square root of 18 is 3 root 2. Now, to think through this one, now the direction is not just 45. We did talk about that it was a 45, 45, 90 triangle. But that is this angle right in here. What we want to know is this angle, again, from the positive x-axis over to that arrow there. So we have to think about how we would do that. So all the way, if I were to go, let me draw this in with a different color here. If I were to go all the way here, that would be 180, but we want to go 45 degrees less than that. So that means we're going to have to do 180 degrees minus the 45 degrees, and that's where we get 135 degrees. Again, if you didn't pause it before, try it on this last one and try it on your own. See what you can do. I'll start D here. So again, I'm going to think of that as the initial point here. We're going to put that at kind of my new origin. And then let's think about the triangle. So it goes to the left 2 and down 3. So that means my component form is negative 2, negative 3. Again, do Pythagorean theorem to come up with your magnitude to find that hypotenuse basically. So 2 squared plus 3 squared, that gives us 4 plus 9 or 13. That equals the hypotenuse squared. So the square root of 13. So now we need to find the direction. So this is a quadrant 3 angle if I'm looking at it here. So again, we want to find all the way around here. Let me just draw that out here so it's a little bit easier to see. Just kind of sketch it here. So we know that this is 2 and this is 3. Really what we want to find is this angle in here first. So we can do the tangent. I'll go right away to the inverse tangent. So we're doing the inverse tangent of 3 over 2. That gives us, on our calculator, 56.3 degrees. So that means right in here is 56.3 degrees. Kind of sloppy, but you can kind of tell where that is. Okay, so we need to think about the direction then. So this is 180, but we have to go 56.3 degrees more than that. So this one is 180 plus the 56.3 degrees. Hopefully all of that looks pretty darn familiar. Now we did it with radians before, but now we're doing it in terms of degrees. So we're just thinking in terms of the 180 or the 360 and where is that arrow going. So it's really, really a lot like the trig that we had solved before. Okay, so it's not a whole lot different. So let's try another example like this. So this one you'll see is kind of similar, just we're not giving you the drawing of it. We're just giving you some other information on here. So given the initial and terminal points of vector AB. So that means A is your initial point and B is your terminal point, if you see the way that the arrow is pointing on there. We want to find really the same three things. One thing that I like to do on this, and you actually won't have to do this, once you get good at this, you may not have to do this at all, but if you ever get stuck, draw yourself a picture of it. It doesn't even have to be a nice picture. The first one, maybe I'll do a nice picture where, I'm going to draw out. So that's -2 down 1, 2, 3, 4, 5, 6, 7. So that is point A. And then 1, 2, 3, 4, 5, 6, and up 1. This would be point B. Again, you don't even necessarily have to do a picture that's that detailed with all the points in there right all the time. I will for the first one, maybe I won't for the second one. Some of you will probably be able to do this without even drawing any picture at all. That's okay. All right, so if we look at this, same idea on here. Okay, so notice I had my initial point and then my terminal at A and my terminal point at B. We want to find the same ideas. So let's think of this in terms of, let me change the colors here. Let's do here and here. Let's think about how far apart they are. So if we are starting at -2 and then going all the way over here to 6, that means that really has a distance of 8 between. Here, if I'm down at -7 and I go up to 1, again, that has another distance of 8. So let's do our component form. Component form is, again, that notation from the initial point, it's going to the right 8, and it's going up 2. So that's our component form. Again, if you look up here, that's the notation, that's absolute value. That is just the magnitude. That's the notation for the magnitude. It's absolute value because that's our distance, how far apart they are there. So to find that, again, we can do Pythagorean theorem. 8 squared plus 8 squared gives us that hypotenuse squared. Or if you recognize on this particular one, it's a 45, 45, 90 triangle. So our magnitude, I'm going to write it in our notation here, is the length of the leg times the square root of 2. You can just start that way. Now you can do trig to find out the direction. Again, really I'm thinking of this. It's not in standard position, but if I kind of thought about it in standard position, again, it's what it's called as a free vector. It can be anywhere on your coordinate axes, and all the other stuff, the component form, magnitude, and direction are all the same. So that's why I'm kind of thinking of it that way. We want to know this angle right here, and we actually already know it. We don't even have to do any work. If you were to do work, you could do the inverse tangent of 8 over 8 or the inverse tangent of 1, which is 45 degrees. Okay, try pausing it, try part B, and see what you can do. Again, you can draw yourself a picture. Some of you may be able to think through it without a picture, and that's okay too. Try it. So I'm going to draw myself a picture. My picture this time is not going to be quite as detailed here. So I'm going to start up at 0, 8. I'm going to think, okay, it's somewhere up here. Obviously, it would be on our y-axis here, but up 0, 8. And -9, -3 would just be somewhere over here. That just at least gives me somewhat of an idea of which direction I'm going. And that's why I sometimes like to draw a picture on there. At least it kind of tells me in general where we're going. Okay? So again, we're going to go through our normal stuff. That means to get our horizontal component right here. If I'm at 0 and I'm going to the left, I'd have to get to -9. So that's a distance of 9. I'm going to the left 9. And then to get down to this point, we're starting at 8, so that's 8, but then we have to go down to -3. That would be 11. So that means we're going down 11 to get to that terminal point there. And that's my component form. Okay, it's Pythagorean theorem to come up with our magnitude. 9 squared plus 11 squared gives us 202, so our magnitude is the square root of 202. Now we need to come up with our angle. So if I think about this, I want to find all the way around here. Okay, so now trig isn't going to give me that entire angle, but it will give me this little angle, basically our reference angle, if you remember that word from Algebra 2 right there. So if we want to find that, again, I'm going to do my inverse tangent of the opposite over the adjacent, and that's going to give me 50.7 degrees. So that angle in there, I shouldn't write so sloppy, sorry, is 50.7 degrees. So we need to know 180 plus that. I'll write that down, plus the 50.7 degrees, and that gives us our direction of 230.7 degrees. Okay? All right. The next part of what we're doing is some basic kind of operations with these vectors here. So you'll see that it's going to look like we're going to do something complicated, but hopefully it's not going to end up actually being as complicated as it looks here. So when we add two or more vectors, the sum is a single vector, and it's called the resultant vector. Okay, the resultant vector. Now, if you watched that quick little video, like it was a 1.5-minute video before this about what it looks like, it kind of gave a nice visual of what it looks like. Really what we're going to think about is the tip to tail. That's what I'm going to kind of demonstrate on here. So if I'm doing, let's demonstrate A. Now, you're not going to have to draw all of these. You'll see that you won't really need to draw all of them all the time, but I'm going to draw the first one here for you. So if I do vector W, I'm just going to go ahead and put it in standard position. So that means my initial point is on the origin. So if it gives you the horizontal and vertical components, that means I'm going to go to the left 4 and up 1. And our vector looks like this. That is vector W. Now, if we are adding vector Y to that, what we're going to do then is from, oh gosh, sorry, from, I guess I zoomed in on that, from that point, from the terminal point of the other vector, I'm going to go from there. So our horizontal component is 2, so I'm going to go 2 to the right, and then vertical component is 5. So 1, 2, 3, 4, 5. Notice from the terminal point of vector W, I added on this vector Y. So now really this is our resultant vector going like this. So this is vector W plus vector Y. So we can count this here. So from the initial point here, it went to the left 2, and it went up 6. So this is our component form there, okay? Now, stop and think about that for a minute. We drew a picture. Do you have to draw a picture? Take a look at W and Y here. Kind of notice something. If you look at the horizontals, -4 and 2, -4 plus 2 is just -2. If I look at the vertical, 1 and 5, oh my goodness, that's just 6. It's really just that easy. So do you really have to draw a picture every time? No, you don't have to. I'm going to draw one more picture for you, though. I'm going to look at the picture for D, just to think about scalar multiplication, and specifically when it's a negative. So I'm going to draw W somewhere else. Once again, I called this a free vector. That really means you can draw it anywhere. So let's, I don't know, pick a point. Let's start W right here. And let's think about, I'm going to move it up a little bit because I'm going to give myself a little more room. I'm going to start it right here. I'm going to go to the left 4, and I'm going to go up 1. So again, this is vector W. Now, if I multiplied it by a negative, all that does is change the direction. So instead of going to the left 4 and up 1, I'm going to go to the right 4 and down 1. So that's just if I were changing the direction on it, if I were multiplying it by a negative scalar number there. But if I'm going to multiply it by -3, that means I'm going to have to do that 3 times. So I'm going to go to the right 4 and down 1, and right 4 and down 1. And this is -3W. Now count it. Again, if you go to the right, that's going to the right 12, and then here that's going down 3. So that means this is, positive 12 and -3. Now look at vector W. What did you do to those numbers? Really? We just multiplied them by negative 3. So it's just that easy. So if I go back to b, I'm not going to draw b. So I'm taking vector z, which I'm going to write the component form for that, negative 3, 0. And instead of subtracting, I'm going to say we're adding times the scalar multiplication of negative 2. So if I multiply y by negative 2, I'm going to have negative 4 and negative 10. So if we add these together, we get negative 7, negative 10, and that is our subtraction. So try C and E and see if you get the same answers I do. All right, I filled in my answers for these couple here. So if I did 4 times W and then added on Z, we should have gotten that negative 19 and 4. And then I filled in the rest of these, so 2W and 4W, and I did, oops, sorry, negative 1, oh my goodness, times Z. So I added that positive 3, 0, and we should have gotten 322. All right, last example. I know I'm talking a lot. We're just trying to squeeze in as much of this as we can to get you prepared for calc next year. So last example is not really that bad. So find the component form of vector v that has a magnitude of 8 and a directional angle of 210. Okay, let's draw this. So if it has a directional angle of 210, that tells us this is 180, 210 is past that. That tells us that my vector is in this direction here. That's what that 210 degrees. Now we also know the magnitude of it. The magnitude of that vector is 8. So this is the terminal point and that is my initial point. Okay, so we need our component form. So we need to come up with some stuff here. So I need to know this and this distance here. Now, this is really just a right triangle. Now, we need to know a little more information about the triangle. We need to know this angle in here. And we should know that. If the whole thing is 210 and right at the horizontal is 180, we know that that is a 30-degree angle. Now, you could either use trig or you can come up with if we know this is a 30, 60, 90, we could do it that way. If I did trig, let's say we wanted to find the y. I could do the sine of 30 degrees is that opposite over the hypotenuse. Okay, and we know that the sine of 30 is 1/2. That gives us that our y value is 4. Okay, we could do the same thing if this is my x right here. The cosine of 30 degrees is the adjacent over the hypotenuse. We know cosine of 30 degrees is root 3 over 2. So that means if we multiply by 8, it's 4 root 3. Now, we also, again, if this is one of our special right triangles from geometry, if we know a 30, 60, 90 triangle, if this is 30 degrees, our short leg is half of the hypotenuse. So if the hypotenuse is 8, our short leg is 4. And then the longer leg is the short leg times the square root of 3. So this helps us now really just come up with our answer, our component form. From the initial side or initial point, we're going to the left 4 root 3. And we are going down 4. All right, that's it for me for today. I talked a lot. Again, try these. They look hard at first, but I think once you get the hang of them, you'll notice that they're not as bad as they originally look. All right, thanks, guys. Bye.